Alright, let's look at part A, 1. They want to know, for the reaction, indicate whether the entropy is positive, negative, or 0. Justify your answer. So when we look at the reaction, it looks like we have 3, there's 2 moles and another mole. That's 3 moles on the reactant side going to 1 mole and 1 mole. So that's 2 moles on the product side. And so that looks like it's more order to me. The other thing is, you notice we have 2 moles of gas on the left, actually 3 moles of gas on the left, and none on the right. So we're definitely becoming more ordered. So delta S is going to be negative. So it's unfavorable entropy. So let's come up with an explanation. So delta S will be negative because there are 3 moles of gas on the reactant side and no gases on the product side. You know, I think that would probably be enough. This is sort of extra. You never know, it's good to be detailed. There are less microstates on the product side. So that would certainly cover our bases. In part 2, they're asking us whether delta H or delta S is driving this reaction. And so if we think about the signs, the delta H, it looks like, is negative 134, and the delta S is, we just predicted that it would be negative. And remember that a negative delta H is exothermic, and it's very favorable. But the delta S being negative means things are becoming, the reaction is becoming more ordered. Is becoming more ordered, and so this is an unfavorable delta S. So let's try to come up with an explanation. So here's my explanation. This reaction is enthalpy driven. So you notice this is the statement. You notice I'm starting with the answer. You got to make a definitive statement of what the answer is, because that's what they asked you. Was it delta H or delta S? So there it is. The reaction is enthalpy driven. Then I say, how do I know it? Well, delta H is negative. That might be enough, but I'm gonna sort of drive it home to make sure that they're not being too nitpicky about the grading. So why does it matter that it's negative? If it's negative, it releases heat energy, and the products are at lower energy than the reactants. So I think that's a pretty solid explanation. Entropy, you notice I'm also going to mention that entropy does not drive the reaction, because they asked us about both of them. And it's because it's negative. Now you might think, do I need an explanation of why it's negative? But I doubt it, because we just explained how we knew it was negative up in part 1. So that should be good enough. In part 3, they're asking us how delta G is affected by temperature. And for that one, you notice we just learned about the delta S and the delta H. And we're going to talk about delta G. So we might as well just get down to it. The Gibbs-Helmholtz equation is the way that we explain our thinking here. So, and actually I'm going to write it up a little bit further away. We saw that delta S was negative and delta H was negative. This is favorable enthalpy because it's exothermic, and this is unfavorable entropy because it was negative. So it's definitely going to be, as we just saw, an enthalpy-driven reaction. But if we do what they're saying here, we have an increase in temperature. You'll notice if we increase the temperature, it's increasing this unfavorable entropy term. So it's likely that delta G is going to become less spontaneous. Now before we write an explanation, we're just thinking out loud about this. Let's go back and see how they asked us to explain it. How is the value of the standard free enthalpy change affected by this? So if it's less spontaneous, there are a couple ways that we could explain it. We could explain it as it's going to become less negative. I don't really like that. More positive. That's better. We could say it's going to become larger, which is true if we're thinking about it's becoming less negative. That means it's going to become a bigger number. So any of those would work. I actually kind of like this one. I think it's the clearest. This one I'm worried that they'll be a little bit confused on. So let's come up with an explanation. Here's my explanation. Delta S is negative. Negative T delta S therefore is positive, because we know that if this is a negative times a negative is a positive. I don't think you have to say that little bit. As long as you say delta S is negative, and therefore negative T delta S is positive, if the temperature is raised, the magnitude of the unfavorable negative T delta S term will become larger, making delta G become more positive. There are other ways to explain this. You could do a Le Chatelier principal argument by putting energy into this reaction. You remember that energy would be, if this is negative, it would be on this side, over here on the product side, because it's giving off energy. It's an exothermic reaction. So if energy is on this side and we increase the temperature, it's going to shift the reaction back to the left. If it shifts it back towards the reactants, the reaction will become less spontaneous, and therefore delta G will become positive. I think that Le Chatelier argument would work just as well, but I think they're hinting at this one because of the sort of flow of going through delta S and delta H and so on. In B, they are saying that some reactions that are predicted by delta G to be spontaneous, as in are favorable to make products, sometimes they don't proceed at a measurable rate at room temperature, account for this contradiction. Now, you'll notice that they're essentially giving you the answer here, right? They're saying that the rate isn't fast enough. So if they're giving you the answer that kinetics is the answer, when they say explain it, I have a feeling they're going to want a specific explanation about kinetics. So what is it in kinetics that explains why reactions go slowly? Well, there's two ideas, and they all come down to collision theory. So in collision theory, you'll remember molecules need to collide with enough energy, so must have enough energy, and the second one is they must collide with the correct orientation. And I think that those are the two that they're going to want you to explain. So let's see if we can come up with an acceptable explanation. So my explanation is the reactants must collide with enough energy to overcome the energy of activation. I think that might be kind of a key phrase there to get credit. If only a small percentage of the molecules have enough energy, the reaction will be slow. And then the second part we said the molecules must collide with the correct orientation. Turned out for grading they only required this one, and they're not specific about if this second one would have been enough in and of itself. So whenever they're talking about kinetics, it's always a safe bet to talk about both of these aspects of it. And the last part, it wants to know what effect a catalyst will have. And you'll remember that delta G and the equilibrium constant K have a very close relationship to each other. They both express how far the reaction will go. And you remember that catalysts speed up the rate of the forward reaction, but they also speed up the rate of the reverse reaction. So they have no effect on the distribution of the two sides. The delta G is what will predict whether you get mostly reactants or products, but the catalyst will only get you to that equilibrium point faster. So I'm going to come up with an explanation. Admittedly, you could probably find a shorter way to say this, but let's see. A catalyst will speed up the rate of the forward and the reverse reaction, and therefore has no effect on the relative amounts of the reactants and products at equilibrium. Therefore, K, the equilibrium constant, is not changed, and since delta G equals negative RT log K, delta G will not change. You might wonder, do you need to say this little bit here? Maybe not. You might get away with not saying that. You might just say right at this point, say instead of that, therefore delta G will not change, and I think it would be fine. It's just if you have time, that's a real safe check to say how the two correspond.